Okay, so on Tuesday, we started lecture set number 9. And lecture set number 9 is the extension of what we talked about in lecture sets 7 and 8. So in lecture sets 7 and 8, we learned about confidence intervals and hypothesis tests for one mean. Okay, so these processes could also be thought of as one mean inference, which was a term that was used on assignment 4 that some students were getting confused about. It basically just means that you're making a statement about a single population mean. So both the confidence interval and the hypothesis test are inferential tools that we can use to make a statement about a population quantity in the most general case. We just happen to be focusing on population means in this course, but you could technically conduct inference about any population parameter. So you could run a hypothesis test about sigma squared if you wanted to. That's an option that does exist. But like I said, we're focusing on the mean in this class. So in lecture set 7 and lecture set 8, we learned about a confidence interval and a hypothesis test, and those are both for one mean. In lecture set number 9, we're studying inference for two population means. So these techniques differ from what we talked about in lecture set 7 and 8 because we are now studying two means at the same time. In the exercise that we left off on, so exercise number 1, we have two populations, which are the dynamic population and the static population. In the dynamic population, we have the number of days that patients spent in hospital post-surgery when subscribed to this particular type of system, so this dynamic or Z-plate system. The other population is the static system. So we're measuring the same thing, which is the number of days patients spent in hospital post-surgery, but they were subscribed to this static system. And the question that we are asking is, does the dynamic system reduce the amount of time patients spend in hospital after surgery compared to the static system? So the question is the mean for the dynamic population less than the mean for the static population? That's what we want to know. And we can answer this question using either the confidence interval or the hypothesis test. Now, obviously, for illustrative reasons, I'm showing both the interval and the test, but we will see at the end that these give a similar answer in terms of what we can expect, in terms of how long we can expect patients to stay in hospital post-surgery. Okay, so just to go over it again, in part A, we're running a hypothesis test about the difference between the dynamic and the static system. In particular, we are asking, is there evidence that the mean amount of time spent in hospital on the dynamic system is less than the mean amount of time spent in hospital on the static system? So you can see in red font right here, I have the hypothesis set up in what I would consider to be the most interpretable way, because you can see clearly from the description that the alternative is mu d less than mu s. So is there evidence that the mean amount of time on the dynamic system is less than that on the static system? In the black font, I have the exact same question. I've just moved the mu s to the other side of the inequality so that we can see the 0 value. Now, both hypotheses are correct. There's not one that's more right than the other. The only difference is preference, and if you like to be able to see the value that gets plugged into the test statistic. Because you can see here, I have the equals to 0, and that's the same 0 that's getting plugged into the test statistic on step 3. Okay, so step 1, declare the hypotheses. This is different from what we had seen in the one sample case because we now have 2 samples and therefore 2 means. Step 2 is the same. We declare the significance level. Step 3, we compute the test statistic. So it's the same step, but the formula that we're utilizing is now different because we have 2 samples of information and we are studying 2 populations. Whereas before, we were only studying 1 population using 1 sample. Again, hence the term one mean inference. So you could think of this in lecture set 9 as 2 mean inference because we're studying 2 means at the same time. Okay, so our test statistic formula is shown in step 3. There's not much to describe here outside of setting the formula up and plugging the values in, and then taking a little bit of care in actually working through the steps of the formula. So that would mean, for example, that we do our fractions first, and then we would evaluate the square root after. That would be one thing where students might get a little bit tripped up, is just making sure that they do each fraction, add it, and then evaluate the square root. Okay, so here we're plugging in, we end up with a test statistic of negative 1.651. From this point, everything is exactly the same as it was in the 1 sample case, because we're either going to take a critical value or p-value approach on step 4. Note that for 2 sample inference, our degree of freedom is the minimum of the 2 sample sizes minus 1. So our sample sizes are 14 and 6. So our degrees of freedom is the minimum of 14 minus 1 and 6 minus 1, which is the minimum of 13 and 5, which is 5. Then for the critical value and p-value approach, we're using the t-table. Our 2 sample inferential techniques are going to be based off of t-distribution. So we're going to be using the t-table to find the critical and the p-value. And this is also done in the same way that it was before. Okay. All right, and then on step 6, we make our conclusion. Okay, in part B, we are being asked to construct a 95% confidence interval for the difference between the dynamic and static systems in terms of the post-operative days spent in hospital. Okay, so this is also going to be done in more or less the same way that we saw before. So on step 1, we're going to find our t value. So here we're going to have a t alpha over 2 on some degree of freedom. Okay. Our alpha value is going to be 1 minus 0.95, which is 0.05. And our degree of freedom, again, is going to be the minimum of n minus 1 versus n2 minus 1, which, as we saw before, is going to be 5. So the minimum of 13 and 5, which is 5. Okay, so therefore our t value is going to be a t on 0.025 and 5. Okay, so we go to our t table. We're going to match 0.25 to 5. And that gives us 2.571. Okay, so the critical value for this test is 2.571. Okay, so then on step 2, we're going to compute our confidence interval. So the formula here is x bar 1 minus x bar 2 plus or minus t alpha over 2 on some degree of freedom. Okay, multiplied by the square root of s1 over n1 plus s2 squared over n2. All right, so this is going to give us 7.36 minus 10.50 plus or minus 2.571. Multiplied by the square root of 1.22 over 14 plus 4.59 squared over 6. This is going to give us negative 3.14 plus or minus 2.571 multiplied by 1.902016, negative 3.14 plus or minus 4.890083. Okay, and then we add and subtract, and this is going to give us negative 8.030 to 1.750. So hopefully you can still see the similarities between these two, the approaches that we're learning here and the approach that we learned in lecture set 7. The only difference is the slight change in the formula to accommodate that extra sample of information. Okay, and then we can conclude. So we have our general statement here. So we are 95% confident that the population mean difference between post-operative days spent in hospital is between, sorry, I'm just going to switch this word up here. We are 95% confident that the population mean difference in post-operative days spent in hospital between the static and dynamic systems is between negative 8.030 and 1.750 days. All right. Not my best conclusion, but so we have this pretty much the same opening part. So we are whatever percentage interval we're studying. So we are 95% confident in this case. Then we're talking about the population mean difference. So we're talking about the difference between the days spent in hospital on each system. So the second part of the statement is trying to illustrate the variable that's of interest to us. So we are 95% confident that the population mean difference in post-operative days spent in hospital between the static and dynamic systems is between negative 8.03 and 1.750 days, which is a pretty wide range. It's basically telling you that if you take the static, if you are using the dynamic system, you could spend between 8 days less up to almost 2 days more in hospital on average, right? So this is quite a wide range in terms of the experience that patients are having in hospital post-surgery on between these two types of systems. Now, the other thing that we can take away from this is since the 95% CI includes 0, there is no evidence that either system, or let's be very specific, there is no evidence that the dynamic system reduces the number of post-operative days. Okay. So since the confidence interval includes 0, it means that the possible difference between the post-operative days between the two systems could be 0, which effectively means that there's no difference between how long you spend in hospital post-surgery on either system. So this interval is not giving us sufficient evidence to conclude that there's actually a reduction in post-operative days if you use the dynamic system. And this, of course, would agree with the hypothesis test conclusion, because from the hypothesis test, we found the same result, that there's no evidence that the dynamic system is reducing how long patients spend in hospital post-surgery. All right. Any questions? Okay. All right. So in the first half, I guess we can call it, of this lecture set, it's about halfway, we learned how to conduct two sample inference. In the second half, we're going to look at another technique for conducting two sample inference. The difference between the two is a structural difference in the data. In the first two examples that we looked at in this lecture set, so the example that we just finished, for example, we assumed that the populations were independent of one another, right? So in the previous illustration, we had our dynamic population and our static population. The patients subscribed to the dynamic system are assumed to be independent of the patients subscribed to the static system, which basically means you wouldn't have any patients that are on both systems. They are separate groups of people. And that's what we mean by independent when talking about the independent two-sample t-test, which is what we had just learned about. So we are making the assumption that we are collecting samples from two populations that don't have any overlap between them. Okay, so they are independent sets of units. What we're going to learn next is how we would conduct a two-sample test and build a two-sample confidence interval if we cannot assume independence. Now, identifying this situation is actually not too difficult because dependent data usually exists in what is called a paired structure. So we are going to be looking at data where the observations are emitting what we can think of as a natural pairing, which basically just means that each observation in the data set is going to give us two values. So rather than having two separate samples of information, we are going to have two different measurements attached to the same observation. All right. So when this happens, we have what is called a natural pairing, and we can no longer assume independence between the samples. All right, so on slide 20, we have an illustration of a data set that emits a natural pairing. So we have a taxi company is trying to decide whether the use of radial tires instead of regular belted tires improves fuel economy. So they equip 16 cars with radial tires and drive them over a course. And then without changing the driver or the car, they just swap the regular tire out for, or they swap the radial tire out for the belted tire. And then they drive the car over the course again. All right. Now, after each lap, they measure the gasoline consumption, or after each test drive, they measure the gasoline consumption in kilometers per liters for each of the different cars, right? And the table below gives us those measurements. So you can see from the table that we actually have 16 total observations, right? So we have N is equal to 16 cars, which are listed across the top here. Okay. Each car is giving us two measurements: gasoline consumption on the radial tire and gasoline consumption on the belted tire. Okay. So that's what we would think of as a natural pairing, or what we would think of as paired data. So for each observation, we have two values. Now, what we are going to be interested in doing here is comparing average fuel consumption on the belted tire with average fuel consumption on the radial tire. Because as you can imagine, a taxi company is probably going to be most interested in using a tire that would reduce fuel or gasoline consumption because they can save money. So we want to run, or inevitably we're going to want to run a two-sample test where we compare the average of the belted tire to the average of the radial tire. But because the values come from the same car or the same taxi with the same driver, we cannot assume independence between each measurement. So what we need to do is use a slightly different kind of two-sample test that takes into account this dependent or natural pairing. Okay, when we set this test up, and we're going to look at the details of it momentarily, but it's actually just a one-sample test. What we do is we construct differences between each of the values. So you can see in this row and this row, I've added the differences between the radial and the belted measurements, right? So here I have 0.1. That's 4.2 minus 4.1 gives us 0.1. Right? Here I've added negative 0.2. That's 4.7 minus 4.9 gives us negative 0.2. Here we have 0.4, same thing again. So the differences are simply one value minus the other for each of the observations. So what we've created is a set of 16 differences. And we usually refer to these as little nd. So the number of differences or the sample size of the differences. Right? And of course, this is always going to be the same as the normal sample size, because for each observation, we're just creating one difference. All right, so with a paired t-test or a dependent two-sample t-test, what we're actually just doing here is running a one-sample t-test on the differences. So this particular test and the corresponding interval are going to be very familiar because we've already studied them in lecture set 8. We're now just applying that technique to the differences directly. Now you can show through a little bit of derivation that this is in fact the correct approach. So on slide 22, what I'm demonstrating here is that, or what I'm indicating is that the mean of the differences will be equal to mu1 minus mu2. If we let little x bar d, which is the sample mean of the differences, if we let little x bar d be an estimate for mu d, which is the population mean of the differences, okay, then we can show that the test statistic, or when we standardize X bar D, this is a T distribution with degree of freedom equal to ND minus 1. So basically, anytime we see a subscript D, I'll just write the word out. All subscript D means apply to differences. Okay, so X bar D is the sample mean of the differences. So that would just mean you add all the differences together and divide by the number of differences. Little s subscript D is the standard deviation of the differences. So this would just be found by applying our standard deviation formula to the differences directly. And then obviously ND is the sample size of the differences, so the number of differences. So you just count how many observations you have. Right. So if we use little X bar D to estimate mu D, we end up with a T statistic when we studentize X bar D, and this is on ND minus 1 degrees of freedom. So the point is our hypothesis test and the confidence interval for the paired data is actually just a one sample test, but it's being applied to the differences. So when we're working with paired data, we basically have now a preliminary step where we compute the differences directly, and then we just run our hypothesis test on the differences. Right. So our confidence interval is going to be found in the usual way. So we start with two assumptions. These are very similar to the one sample case. So we're going to assume that the sample of differences are a random sample. So we're still assuming that each observation is randomly selected, but each observation contributes 2 values now rather than 1. Furthermore, we're going to have our same normality assumption. So this can be found either by checking the distribution of the differences using a plotting tool, for example, or if we have more than 30 observations, then the central limit theorem will apply approximate norm, will allow us to assume approximate normality. On step 1 of the confidence interval, we find our test statistic or our critical value. This is found in the usual way. So it's a T on alpha over 2 with ND minus 1 degrees of freedom. On step 2, we build our confidence interval. And you can see that this is pretty much, as I mentioned before, just a one sample interval, but the subscript Ds are indicating that we're working on the differences directly. And then on step 3, we interpret the interval. Okay, our hypothesis test is our usual 6 steps. It has the same assumptions as the confidence interval. I've written the 3 different types of hypothesis tests that we can utilize under step 1. These are just the two-tailed, upper-tailed, and lower-tailed tests about the differences. Okay, so the only difference here is that we are referring, or the only really unique aspect of this testing structure is that the data is paired, and we are now testing the differences between each pair of observation or each pair of values for each observation directly. Step 2, significance level. Step 3, test statistic, usual form. Step 4, p-value or critical value. This is going to be done in the same way that it was done before. Step 5, decision. Step 6, conclusion. So there's really not a lot of difference between how we're handling this test and interval compared to what we've seen before. The big difference is just identifying that you are working with paired data. And then once you've identified that, making the necessary calculations to build the test statistic and the confidence interval. All right. So for our taxi cab example, we want to know at the 5% significance level, is there evidence that the radial tire consumes less fuel than the regular belted tire? And we want to then compute a 90% confidence interval for mu D. On slide 25, I've given the same table that I gave before. So we're starting from the point that we have 16 different observations, which are 16 different cars. For each car, we have the fuel consumption in kilometers per liter, right? So the more fuel efficient car is going to have a higher value because it's implying that you go further for the same amount of gas. So what we would like to know is there evidence that the average fuel consumption of the radial tire is, well, we would like to know if the fuel consumption of the radial tire is less than the fuel consumption of the belted tire. So what we would like to know is, do cars travel further per liter of gas on the radial tire compared to the belted tire? All right. So because we have a paired structure, we're going to start by computing the differences, which I went over before, but just as a reminder here, I'm just taking radial minus belted in each case. Okay, and I'm just following this through. So I'm just going radial minus belted. I have a difference, and I'm doing that for each car. The direction of the difference here is radial minus belted. Now, when we're working with paired data, you can construct the differences in either direction. So here I'm going radial minus belted, but we could also go belted minus radial. That's not incorrect. The only difference is how you would set up the hypotheses depending on which direction you work in. So we are taking radial minus belted. If radial tire is more fuel efficient than radial values should exceed belted values. Therefore, XD or mu D bar should be greater than 0. Okay, this is the part that usually trips students up the most because I think they just have a hard time understanding why the direction matters and how this influences the hypothesis test. So in this situation, we're measuring fuel efficiency, but we're measuring it in kilometers per liter. So the values, our raw data values, are telling us how far the car travels per liter of gas. So the more fuel efficient tire is going to travel further per liter of gas. Since I've constructed the differences as radial minus belted, and I want to know if the radial tire is more fuel efficient. In this situation, the expectation would be that the radial measurements are bigger than the belted measurements. So the expectation then would be, if I subtract the belted values from the radial values, these numbers should be bigger than 0. Okay, so therefore, I am going to be interested in testing if the mean of the differences is greater than 0, because the differences are found by subtracting the belted values from the radial values. So had I have done it the other way, so say I subtracted belted from radial from belted, so I have all my differences were now reversed in sign, I would be conducting a lower tail test, because then the expectation would be that the differences are all less than 0, since the radial measurements should be bigger than the belted measurements if the radial tire is actually more fuel efficient. Right, so it's quite a bit to think about, but the point is you need to pay attention to the direction in which you compute the difference. Because if the test is not two-sided, then the direction in which you compute the distance is going to determine the direction of the sign in the alternative hypothesis. Right. Any questions about that? So good. It's not a question. Just kidding. I'm Ron Burgundy. Okay. Good stuff. So now we'll look, I have two examples of the test and the confidence interval. I've just written these ones out because we've seen a lot of hypothesis tests and we've seen a lot of confidence intervals at this point. So just for a little bit of a break from writing everything, I've just given the steps. The most important part here really is that preliminary setup. So we built the differences for this particular data set. Now, in order to construct the test statistic and the confidence interval, we need to have X bar subscript D, little s subscript D, and little n subscript D. Little n subscript D is the easiest because it's just the sample size. So we have 16 differences. So little n subscript D is 16. X bar subscript D is the mean of the differences. So I'm illustrating how that would be calculated here. And this is not meant to confuse anyone, but it's literally just adding the differences together and dividing by the number of differences. It's just the formula for the sample mean being applied directly to the differences, right? So you can see here, I have 0.1. That's the 0.1 here, negative 0.2, negative 0.2, up to negative 0.4. Oh, sorry, this should be a 3. Up to negative 0.3, and then 0.1, 0.1. Right, just add the differences together and divide by the number of differences. That gives us the average of the differences. The standard deviation of the differences can be computed using the defining formula or the computing formula. So I'm giving the defining formula here, but you could also just apply the computing formula to the differences directly. Okay, and in doing that, you end up with 0.2272114. So again, this is just standard deviation of those differences. So it might almost be easier to think of a paired t-test as a process where you start by computing the difference between each paired value, and then basically just pretend like that original data didn't even exist and treat that paired value as those and treat those differences as a sample. So now my sample is just this collection of differences, and I'm just going to do what I usually do in the one sample case to the differences, because that's all the paired t-test really is. Right. Once we have our X bar D and SD, in some cases, these might even be given to you, but if they're not, you just compute them using our usual formula for mean and standard deviation. Then we can check the assumptions. Okay, so we're going to assume the cabs are randomly selected. And then let's assume that we check the differences using a QQ plot and they looked normal. On step 1, we set up our hypotheses. So we're using an upper tail test here. Ooh, this is an equal sign. Oh shit, did I have that? Yeah, these are all equal signs. Okay, so then we set up our hypotheses. Again, we're doing an upper tail test because of the direction of the differences that we computed. If we had gone the other way, this would now be a lower tail test. Okay, step 2, significance level. Step 3, compute our test statistic. Hopefully you can see that, again, this is just a one sample test applied to the differences. So we're just plugging in to our formula for the test statistic, and that gives us 2.310. Step 4, we find the critical value. So in this case, we're doing an upper tail test, alpha 0.05 on 15 degrees of freedom. So if we go to our T table, we can confirm that this is 1.753. So here's 0.05, 15, 1.753. Okay. So that's just found in the usual way. All right. And then if we wanted to take the p-value approach, this is also done in the usual way. So if we sketched out our T curve, here's 0. Here's our test statistic, 2.311. This is the area of our p-value. Okay, so p-value equals probability t greater than 2.311. Right. So hopefully this all looks very familiar at this point, or is starting to look familiar. Right, so now we would just go to our T table. We have 15 degrees of freedom. We're looking for 2.311, which is going to be in between these two values here. So in this case, the probability that t is bigger than 2.311 is between 0.025 and 0.01. So therefore, the p-value is between 0.025 and 0.01, which is what I have here. All right. So in this case, since the p-value, anything in this range for the p-value is less than alpha, we can reject. And since our test statistic is greater than the critical value, we can also reject. So then on step 6, we can conclude that there's evidence that the radial tire is more fuel efficient than the belted tire on average, which means that it would be advised that you equip the cars with the radial tire. Even if they're more expensive in the long run, it would save money, right? All right, in part B, we're computing a confidence interval. And again, this is going to be done in the usual way. So we have T alpha over 2 on ND minus 1. We're computing a 90% interval, so alpha is 0.1. So we have T on 0.1 over 2 comma 15, which is T 0.05 on 15, which we actually looked up in the previous question. So that gives us 1.753. On step 2, we just plug into our interval. And then on step 2, we plug into the formula for the confidence interval. So that gives us 0.032 to 0.231. So we can say that we are 95% confident that the radial tire gives an extra 0.031 to 0.231 kilometers per liter on average compared to the belted tire. And we're able to embellish a little bit in here and say, they provide an extra because this interval does not include 0. It's a strictly positive interval, which implies that there is a difference in how far the car travels on the belted tire, even though it's maybe not that significant. The 0.2 of a kilometer over a long run could be helpful. Right. Any questions? Okay. Okay, so we'll look at another illustration here. So we have a study of the factors affecting milk production in cows was conducted on a dairy herd. One part of the study involved 8 randomly selected cows being fed their usual diet for a month, then a new diet for the next month. The average production in liters under the 2 diets is given below. All right, so we have 8 different cows that were randomly selected, and each of the 8 cows was fed a different diet for a duration of 1 month. Okay, so they have the current diet. We might want to think of this as original or old for 1 month, and then they have a new diet for another month. And we want to know, well, what we will eventually want to know is if this new diet has increased milk production. So we're measuring milk production in liters in this example. All right, so this again, if you ignore the difference column for, I just blocked it with my arm as if you guys could see that. Okay, so if you ignore the difference column for now, so just imagine this wasn't here just momentarily. Okay, this would be an illustration of paired data, right? So we have 8 cows, each cow is contributing 2 measurements, and we're interested in determining if there's a difference between the 2 measurements. So we cannot assume independence here because the measurements come on the same cow. So we're going to be using a paired t-test. So the first thing that we're going to do is construct the differences. Okay, so I have decided to take the differences as new minus current. So 7 is 46 minus 39, 9 is 41 minus 32, -2 is 39 minus 41, 1 is 47 minus 46, 8 is 35 minus 27, -4 is 29 minus 33, +4 is 35 minus 31, +7 is 39 minus 32. Okay, so the direction of the difference in this case is going to be new minus current, right? And again, it's important that we establish the direction the difference was taken in, because this is going to influence, or this is going to determine the direction of the alternative hypothesis in the situation that we are not doing a 2-sided test. So in part B, it says, given X bar equals 3.75 and SD is equal to 4.89, and all assumptions of the paired inferential procedure are intact, is there evidence that the average milk production increased on the new diet at the 5% significance level? Okay, so in this situation, we want to know if the new diet is increasing milk production. Our differences are new minus current. So would we expect the differences to be bigger than 0 or less than 0 if milk production has increased? Yeah, sweet, bigger, good. Okay. I was kind of like staring into the void and just wondering, will they respond? Yeah, exactly. We would expect it to be, it did, it was terrifying. We would expect them to be bigger. And again, this is simply because of the direction we took the difference in. We could ask the exact same question, but do current minus new. Had we done current minus new, this would just turn into a lower tail test. So it's really important that we understand how the differences were computed so that we can, basically it gives us the flexibility to set up the test in whatever way we want. Like if you're not doing a 2-sided test, you can always make paired t-tests upper tailed, which maybe you have a preference for. So that's why this direction thing is very important. Okay, so we're basically going to just run an upper tail test at the 5% significance level. And then part C asks, will a 90% interval contain 0? yes or no, and then to verify it. So we're going to run the test and then use the test to determine if the interval will contain 0. And then we're going to show whether or not that is actually the case. All right, so step 1, we're going to have H naught. It said in the question all assumptions are intact, so I'm just going to skip that and go right to the test. You can tell that I'm a little bit lazy about that with lecture stuff. Okay, so on step 1, we have mu d equals 0 versus HA mu d greater than 0. Step 2, we have alpha equals 0.05. Yep. Step 3, we have T is x bar d minus mu d over SD divided by the square root of ND. So this is going to be 3.75 minus 0 divided by 4.89 over the square root of 8, which gives us 2.169. All right. Okay, so then on step 4, we can take our critical value approach or the p-value approach. Okay, so if we take the critical value approach, we're going to have a t on 0.05 and 7. All right, so if we go to our t table, we're matching 0.05 to 7, and that gives us 1.895. All right, so we can see that in this case, the test statistic is clearly inside the rejection region. So we'll be able to reject based off of that approach. All right, and then if we take the p-value, okay, so here we're going to mark down our test statistic. All right. So in this case, the p-value is equal to the probability that t exceeds 2.169. Okay, so if we go to our t table, we have 7 degrees of freedom. 2.169 is here. Okay, so we can say since the probability that t exceeds 2.169 is between 0.025 and 0.05, our p-value is going to be between 0.025 and 0.05. All right. Okay, so then on step 5, regardless of which approach you take, we can reject H naught. So you can reject H naught based off of the critical value approach or the p-value approach. Those are always going to agree. All right, and then on step 6, we can say at the 5% significance level, the data provide sufficient evidence to suggest that the average milk production increased on the new diet. And okay, so that's an illustration of a paired two-sample test. And hopefully what you can see is that this is basically, again, it's just a one sample test being applied to the differences. So once you compute the differences, you can basically just throw out the raw data and just treat the differences like a single sample. And then as long as you know the direction in which you computed them, everything else will be just like a one sample test. And if it's a double-sided test, it doesn't even matter which way you compute the differences. Like you obviously want to be consistent from observation to observation, but then you don't actually need to worry about it, because if your testing does not equal, it doesn't matter if you go this way minus this way or the other way when subtracting. Okay, in part C, it asks, will a 90% confidence interval contain 0 and to verify? Okay, so the first thing we need to consider here is for a 90% CI, T alpha over 2 ND minus 1 is T 0.05, 15, which is 1.895. All right. So the upper tail 5% hypothesis test and 90% CI use the same critical value. All right, so you can see that the critical value we used on step 4 of the hypothesis test is the same as the critical value that the 90% confidence interval will use. Now, basically, when we're comparing the result of an interval to a hypothesis test, we need those two values to agree in order for the conclusion to agree. So since we have the same critical value in the interval as we did in the test, they're going to give us the same solution. If those two values are different, then we can't guarantee that the solutions will be the same. All right, so in this case, we have the same critical value. So then the question is, will the interval contain 0? All right. Well, we know that the interval and the hypothesis test are going to agree because they use the same critical value. The hypothesis test told us to reject the null. So reject that mu d is equal to 0, and that there's evidence that the mean might actually be greater than 0. So since we rejected H0 mu d equals 0, then the interval will not contain 0. In fact, the interval will have I need to use the word two, will have positive bounds. Okay, so the hypothesis test gave us evidence that mu d is bigger than 0. Since the critical value for the interval and the test are the same, the interval is going to give us the same conclusion. So in order for the interval to give us evidence that mu d is bigger than 0, it's going to be an interval with positive bounds that does not include 0, because then the interval is basically telling us the difference is between this positive number and this positive number, which means that it must be bigger than 0. Okay, so we can verify this simply by building the interval. So x bar d plus or minus t 0.05 on 15 multiplied by SD over the square root of ND. So we have 3.75 plus or minus 1.895 multiplied by 4.89 over the square root of 8. That gives us 3.75 plus or minus 3.276. 22. And now you can basically see that this is going to work out, because when you subtract this value from 3.75, it's still bigger than 0. So this is going to give us 0.474 to 7.026. Okay. And that's kind of, I don't know, this is the more interesting stuff that you can do with the interval and the hypothesis test, in my opinion, because you're actually starting to, if you're able to understand this, it means that you have a little bit deeper understanding of how the two are related and how you can basically determine the outcome of one from the other. Like, for example, here, if we had started with the interval, so if I had said to you, I subtracted, or if I had told you the direction of the difference in this problem, and then I said to you, okay, here's the 90% confidence interval. Will the one-sided test at the same significance level result in rejection of the hypothesis? You could answer true, because the interval is telling you that there's evidence that the mean is different from 0 because it doesn't include 0. And it's telling you that there's evidence that the mean is greater than 0 because they're two positive bounds. So you're actually able to infer the result of the other procedure based off of what you have seen from either the test or the interval, which I think is neat. And it also serves as very good multiple choice questions for the final. So, you know, this type of thing is something you might want to review beforehand. Okay, awesome. Any questions? Lecture set number 9 and lecture set number 10. Can we do it after? Cool. Any other questions about the material? It's in your student system. I think it's like December 16th or December 18th or something like this. Yeah, December 16th. And it's a morning exam, I'm pretty sure, 9 a.m. to noon. No, 9 a.m. this time. Okay. So I'm going to start lecture set 10, just to get as much of it done as we can with the last 15 minutes. Okay, so lecture set number 10 is devoted to hypothesis tests. So we're going to study two hypothesis tests, the chi-square goodness of fit test and the chi-square independence test. Okay. So we're only looking at hypothesis testing in this lecture set, and it's hypothesis testing in two different situations. But the easy way to identify these tests, as you're going to see when we look at examples, is that they're run on counts. So they're hypothesis tests for categorical data. So in the second case, when we talk about the independence test, that data will always appear in a contingency table. And in the first case, when we talk about a goodness of fit test, you can think of that as a frequency table. So it's the goodness of fit test is like a hypothesis test for a frequency table or a frequency distribution. And the independence test is a hypothesis test for a contingency table. Both of these tests are run using the chi-square distribution. Okay, so the chi-square distribution is a continuous probability distribution. So it's the same type of distribution as the normal and the t. However, the chi-square distribution is a right-skewed distribution. So it only exists for positive values. So the lowest value a chi-square random variable can take on is 0, and the highest value it can take on is positive infinity. So when we are running a chi-square goodness of fit test and a chi-square independence test, we are going to be utilizing the chi-square distribution, which means that we are going to be utilizing a chi-square table, which is given in the course content section, and it looks like this. It again has 2 pages like the t distribution, except these 2 pages would not stack vertically, they would line up horizontally. So the chi-square table would be read left to right, whereas a t table is read up to down. But the way the chi-square table works is exactly the same as the way the t table works. And we'll see more examples of this in a little bit. All right. A chi-square distribution, like a t distribution, has a degree of freedom associated with it. The degrees of freedom is calculated differently for the goodness of fit test and the independence test, but it's a very easy calculation. This slide, so slide 4, gives a few different illustrations of what a chi-square curve would look like, just for a little bit of background information. But for the most part, we're just going to be sketching right-skewed curves when we illustrate the critical value and the p-value approach. The big thing here is just that the chi-square is strictly positive, so it goes from 0 up to infinity. Okay, so 0 is no longer at the center. We actually don't know what the center is for the chi-square as it changes for each degree of freedom. So it's always just going to be kind of rough sketches. You can see that the role of the degree of freedom is basically it pushes the peak down and it pushes the mode out. So you might be able to argue that for a fairly high degree of freedom, you would have a chi-square curve that mimics a normal curve at the corresponding center, but the normal curve would still stretch infinitely in each direction, whereas the chi-square curve would stop at 0. But it might be enough of an approximation that you can use it depending on the problem. All right, so I mentioned before that since we're working with a different distribution, we have a different set of tables. Okay, so the chi-square table is the third of the 4 different tables that we're going to utilize in this class. Again, it's a 2-page table that's read left to right. So the t table is read up, down. Chi-square and normal tables are read left to right. The last table that we'll see is called the F table. I think we might get to that next week. And that table has 8 pages associated with it, and it's read in both directions at the same time. All right, so our goodness of fit test is used to determine if a set of frequencies adhere to a pre-established pattern. So the goodness of fit test has a very unique purpose. We're no longer asking a question about a population parameter like a mean. We're asking, do the data that we have collected follow the pattern that we would expect them to follow? So there's a few different basic illustrations of when you could use a chi-square test. One of them would be determining if a die is fair. So if you have a 6-sided die, the expectation would be that each number rolls the same probability of the time, or the same proportion of the time. So a 6-sided die is going to show you a 1 out of 6 times it's rolled. It's going to show you a 2, 1 out of 6 times it's rolled. It's going to show you a 3, 1 out of 6 times that it's rolled, etc. We can use the goodness of fit test to determine if a die is fair, that is, if it adheres to these proportions. If we roll the die, say, 100 times or 200 times or whatever. Right. So the purpose of this test is, again, to determine if some outcome is is adhering to what we believe it should adhere to, which typically just means, like, are the events corresponding to the proportion of times that you would expect them to correspond to? Okay. Like any hypothesis test, the chi-square goodness of fit test can be run in 6 steps. One of the other things that's nice about this test is that we don't have a concept of being two-tailed or lower-tailed or upper-tailed. All chi-square tests are run in the upper tail, so the skewed tail of the distribution. So there's no concept of dividing alpha by 2 or anything like that. It's always run as kind of like a one-tailed test where you operate in the skewed part of the chi-square curve. Like any other hypothesis test, we have a set of assumptions that are associated with the test. These assumptions are all expected frequencies are greater than 1. We're going to define the expected frequencies in a little bit. No more than 20% of the frequencies are less than 5, and an SRS was collected. Our hypotheses for the goodness of fit test in general would be H0, the variable follows the pre-established or specified distribution, versus HA, the variable does not follow this distribution. Now, we can write these hypotheses in a variety of different ways, but this is the general test that we are interested in. Step 2, significance level. Step 3, test statistic. We'll go over the construction of the test statistic in detail. Step 4, critical or p-value, just run using the chi-square table this time rather than the t-table or the normal table. Step 5, decision, usual rules. Step 6, interpretation. Okay, so the test statistic for our chi-square test is x squared equals the sum of the observed minus expected frequency squared divided by expected. This test statistic has little c minus 1 degrees of freedom, where c is just the count of the number of observed values. So c and the sample size are not the same thing. Okay, so note c does not equal little n. Okay, so the sample size and the number of observed values are not the same thing. The number of observed values is basically the number of outcomes. So for example, if I rolled a die 500 times, my sample size would be 500, but the number of unique outcomes would only be 6, because there's only 6 possible outcomes on the die, but I can roll the die as many times as I want. Okay, so C is basically the number of things that can pop up in the experiment, but it's not the same thing as sample size. Our critical value and p-values are going to be distributed on C minus 1 degrees of freedom. Okay. And our expected values are going to be the sample size times the pre-established probability of observing each outcome. And again, I'll show lots of examples of this momentarily. Okay. So here's an illustration of when we would use this test and how these calculations would work. Let's suppose that, and I think this is actually true, M&M and Mars report that in every bag of M&Ms, 30% of the bag should have brown M&Ms, 20% should have yellow, 20% of the bag should be red, 10% orange, 10% green, and 10% blue. So this is our pre-established distribution. Okay, the proportion of colors of M&Ms in a bag. We randomly select 3 different bags of M&Ms. We dump the M&Ms out onto the table. There's 509 total M&Ms on the table. And before we eat them, we count the number of different colors. So in our sample of 509 M&Ms, we have 152 brown, 114 yellow, 106 red, 51 orange, 43 green, and 43 blue M&Ms. Okay. All right. The question is, do the 3 bags of M&Ms give evidence that the color distribution that M&M and Mars reports is actually not correct at the 5% significance level? So is there evidence that one of the percentages given in the first table is incorrect based off of the sample? Okay, so before we run the test, we need to compute the expected values. The expected value calculation is shown here. So basically what we're doing is we're taking our sample size, which was 509, and we're multiplying that by the pre-established color distribution. So the expected number of brown M&Ms in the 3 bags would be 509 times 0.3. Because if it's true that 30% of the bag should be brown M&Ms, then 30% of our sample size should also be brown. So we would have 509 multiplied by 0.3, which is 152.7. And then it's the same calculation for the other colors. So if it's true that 20% of the M&M bags will be yellow, then 20% of the 509 M&Ms that we're working with should also be yellow. So 509 times 0.2 is 101.8. And then the same thing for the reds. If it's true that 20% of the bag should be red, then 20% of our sample size should also be red. So we would expect 101.8 of our M&Ms to be red. And then for orange, green, and blue, 10% should be those colors. So therefore 10% of our 509 M&Ms should be orange, green, or blue. And that means that 50.9 of our sample size should be orange, green, or blue. Okay. So the expected quantities are found by taking sample size and multiplying by the probability of each of the different outcomes in our distribution. Okay, the next thing that we're going to do is check the assumptions of the test, but obviously I only have a minute left. So I'll stop here for today, but on Tuesday, we'll pick up here, work through the test. We'll look at 2 examples of a goodness of fit test, and then we'll look at a few examples of the independence test, and then we'll move on to lecture set number 11. All right, so have a good weekend, and I will talk to you guys on Tuesday. Yes.